Hello Year 11s and welcome to the Summer Revision Series. These set of videos hopefully are created so that we can go over some of the content that we didn't do so well in over the course of the year and give you an opportunity to go and revise over those topics. So the first topic we're actually going to be looking at is differentiation and calculus, because this is going to be leading into a lot of the stuff we're dealing with in the next year for Year 12. Now, first of all, let's just quickly talk a bit about what a derivative is. Now, in this course, I'm going to try and cut out a lot of the kind of theory-ish stuff and focus more on the practicals and give you a few practical skills here and there. That's the aim of this course. So I'm going to try and limit this as much theory as possible because we've done it earlier this year. Now, what is a derivative? Now, in class earlier this year, when we talked about what a derivative was, we talked about a few things. Now, first of all, it is a rate. It describes a rate of change. So a derivative describes a rate of change. So how quickly is a quantity changing with relation to another one? So how quickly are two quantities changing? How quickly are quantities changing? The other one that we talked about is that this is a gradient function. Our derivative is a gradient function. It tells us how steep a function is at any given point. So here, what we can actually notice is that, like any function, we can actually substitute values of x in. So here, it's our gradient function, and we denote it using f dash x. And so here, when we use our gradient function, f dash of x, our input, we put in x values. Our output is we get the gradient of the tangent at that x value. So a derivative describes a rate of change, so how quickly are two quantities changing with relation to one another, and also it is our gradient function. It tells us what the particular gradient of a tangent is at a given point. And so here, this leads us to our definition of the derivative. So here, this is a definition of what our derivative is. Our derivative is just a limit as h goes to 0 of f of x plus h minus f of x over h. Now this formula is not on your formula sheet. So this is not on formula sheet. Not on formula sheet. So you might need to remember it for the HSC, but in the recent HSC exam, it actually started off and wrote down this equation for you, so you didn't need to remember it. Now, what does this actually talk about? And we talked about this a bit in class, but basically, if I have a look at this limit, it involves two things, f of x plus h, which is that blue quantity. Now, what that just means is if I have my function here, so I've drawn a function here, y is equal to f of x. If I've drawn this function here, f of x plus h is just the y value that would happen at x plus h. So here, this y value, this is f of x plus h. And f of x is just a y value at a random point that we're going to call x. Now, if we want to find the derivative of f of x, we first need to use this method and we approximate the gradient. If we want to find the gradient, we approximate. So we start off by approximating it and we end up getting this line between these 2 points. And so this is our approximation. Now, as you notice, this isn't a very good approximation. So what we want to do is we want to make h smaller and smaller and smaller. So you notice there's this actually distance here of h. What we'll notice is as h gets smaller and smaller and smaller, so if we move our x plus h closer and closer towards f of x, what you'll notice is that dot, let me go back, that blue dot that we had for f of x plus h, that moves closer and closer to f of x. And as we do that, that means, so f of x plus h is now here, that means that our gradient is going to get more, our approximation is going to get more and more accurate and a better approximation of the gradient at f of x. So here, notice our second line, this second red line, this is a little bit better at approximating the gradient. Now, in terms of practicality, all we need to do when we're dealing with these questions is we substitute these values in and take the limit. Now, what I have a note here is do not use this method unless specified to. So if the question specifies that you need to differentiate, and the phrase that they're often going to use is from first principles. So here they have a phrase underneath, from first principles. If they tell you to differentiate from first principles, then you use this method. Otherwise, don't bother. Don't bother. Differentiate using the rules and tips that we're going to use in the following section. Okay, so I'm going to just copy this formula down so that we can have reference of it. Oh, that didn't fully copy down everything. Let me try that again. So I'm going to copy this and bring it down. We're going to be using this formula when we're differentiating from first principles. So I'm going to just pull this down a bit and I'm just going to paste it over here. Okay, this is the formula we're going to use. The derivative f dash of x is equal to this limit of f of x plus h minus f of x over h. So we're going to actually find the derivative using this formula. So the first example, we're going to differentiate from first principle. F of x is equal to 5 minus 2x. Okay, just to help us out, notice in our formula we've got f of x plus h, this blue part, and also this red part, f of x. Now here, we've already got f of x, so we've already got that red part sorted for us. What we need to find is f of x plus h. So what we do is we substitute x plus h wherever we see x in my formula, in my function. So notice here, we've got an x over here. So all I'm going to do, if I want to find f of x plus h, is I'm going to write, well, my 5 doesn't change, but I'm just going to replace wherever I see x with x plus h. Now I can simplify this a little bit further. I can rewrite this. This just becomes 5 minus 2x minus 2h by expanding out the brackets. Okay, now that I've got that, I'm going to put them into my formula. So my derivative is equal to f dash of x is equal to the limit as h goes to 0 of f of x plus h minus f of x over h. And all I need to do is substitute f of x plus h and f of x into here, this formula. So all that becomes is limit as h goes to 0 of 5 minus 2x minus 2h. That's for the first part. So this f of x plus h, that's here, minus f of x, which was my original function. So minus f minus 2x, which is my original function up the top there. And that is a fraction all over h. Okay, now I'm going to simplify the numerator. With these questions, what you're going to notice often is a few terms are going to cancel out in your numerator. And then once you've done that, you're going to be able to cancel out a common factor of h from a few of those terms. So let's actually cancel out a few terms. So I've still got this limit at the front. I'm going to expand out my bracket. So here it's going to be 5 minus 2x minus 2h minus 5. That minus 2x becomes a plus 2x over h. And so here, I can start cancelling out a few terms. Notice in the numerator, we've got this 5 and a negative 5. So those will cancel out. At the same time, I've got a minus 2x and a plus 2x. So all I'm left with in my numerator is minus 2x here. So I'm just going to rewrite this. This is the limit as h goes to 0 of negative 2h over h. The h's will cancel out because we've got this common factor. So that just gives me a limit as h goes to 0 of negative 2. Now when I'm dealing with limits, all I need to do is substitute that h into my, wherever I see h in my function part. Luckily for me, there's nothing there. So this just becomes minus 2. So here, what we did was we found f of x plus h. We found f of x, which was our original function to begin with. We put it into our first principles formula, and then we started working around with that, simplifying and cancelling out terms until we could substitute our limit, and we got our final answer of minus 2. I'm going to do another example with you guys here. So the next example is f of x is equal to x squared plus 3x. Now I'm going to bring out my formula again just so I can see it. So here's my formula. The derivative is equal to the limit as f of x plus h minus f of x plus h minus f of x over h. Okay, so just like I did the first time, I'm now going to find f of x plus h. So what that means is wherever I see x in my original function, I'm going to replace it with x plus h. So here we go. Here we started off with x squared. That just now becomes x plus h squared. Okay, cool. In my function, I had plus 3x. So here we've got another x. I'm just going to replace that with x plus h. So this becomes plus 3 bracket x plus h again. There. Now I can expand this and simplify it. So I'm going to do that. So I'm going to go expanding this. This becomes x squared plus 2xh plus h squared using my perfect square expansion plus 3x plus 3h. Okay, I'm going to leave it like that. Now that I've done that, I'm going to put this all into my formula. So I'm going to just write it out. My derivative f dash of x is equal to the limit h goes to 0 of f of x plus h minus f of x all over h. So that's my formula. Now I'm just going to write in f of x and f of x, f of x and f of x plus h, what I had from here. So here, that becomes the limit as h goes to 0 of f of x plus h, which was the thing I expanded at over here. So I'm just going to write this in. X squared plus 2xh plus h squared plus 3x plus 3h. Ooh, longer section. I'm going to underline it just so we can see which part, where it comes from. Minus, well, I'm going to put this in the bracket as well, f of x, which is my original function. So f of x is just up here. My function says minus bracket x squared. Ooh, let me pick black again. X squared plus 3x. So that's my original function. And that is all over h. Okay. Now that we've done that, we're going to simplify a few things. So we're going to expand out the bracket. So this becomes limit as h goes to 0 of x squared plus 2xh plus h squared plus 3x plus 3h minus x squared minus 3x by expanding out that last bracket. Okay. What can we do here? Now we can start cancelling out a few terms. Now notice I've got this minus x squared over here. That can cancel out with my x squared at the front. Minus 3x is going to be able to cancel out with my 3x over here. Okay, so what am I left with? I'm left with, that's equal to the limit as h goes to 0 of 2xh plus h squared plus 3h over h. Now what you notice is all of these terms in my numerator, they all have a h in them. So I can just cancel out the h from the bottom from all of these terms. And so as a result, I'm just going to be left with the limit as h goes to 0 of 2x from my first term plus h plus 3. Okay, now that we've gone to the step to deal with the limit, we just substitute h is equal to 0 wherever I see h. Now, if you have a look, I only have a h over here. So I just replace that with a 0. And what am I left with? 2x plus 3. And there we go. That is how we calculate the derivative of our function x squared plus 3x. So here are two examples. There was a third. I'm not going to go through that. Here are two examples to help you go through these questions. Now, with these questions, what you sometimes need to do is a little bit more algebraic work to actually get to applying first principles. But hopefully that was helpful going through what differentiation by first principles is.